So this is a fun topic. Welcome, Juan Diego. So we already spent a lot of time talking about B-tree indexes, and we basically talked about them as deeply as we're going to. You'll have to delve a little bit more deeply on the assignment into how they work, but it's basically going to be extensions of everything we saw in class. So I don't think it's going to be too hairy. I mean, it's always hairy to implement these kinds of things, but it shouldn't be too horrible. What I wanted to talk about today, though, is another kind of index, hash indexes. And we talked a little bit about these before, that hash indexes are really good for equality-based lookups, but unfortunately, since you can't use them for range queries, they're not that particularly useful. They get used a lot when you have things like key value stores and you need to look up things based on keys, and you want to use hashing so that it's even faster than B-trees. Let me see what I say here. So direct access, only a small number of block reads. Remember, it is basically the number of levels in your B-tree index. So if you have a reasonably good fan out on your B-tree nodes, and you, even with a very large number of records, you might end up having 3 to 5 disk IOs just to get to the particular record that you want. And then, of course, you have to go look it up in the table. So maybe 4 to 6 IOs, just as a ballpark of what a B-tree would do in those situations. But we can also do hashing, and in this case, you would expect hashing to maybe have that. You still have to look up the record in the table, so that might be 1 or 2 disk accesses for that. But for the hash index, maybe you can do it in 2 disk IOs as opposed to 4 or something like that, because hashing can be very effective at sending us to exactly the block that will hold the record for us. So hashing can be very appealing in certain situations. Now, we talked before about how you build hash tables in memory, and of course we have a couple of different approaches for it. I guess I'm going to talk about that on another slide. But remember, there's open addressing, where the hash function tells us where to start looking, and then there's also bins, which these things have names, and we'll talk about these in a second. But that hash function is pretty important. We need to hash our keys in some way, and then we get a value that tells us basically where we want to look. And so the hash function does have some things that we need to pay attention to. It needs to generate a nice uniform distribution. And so that's what I have here. We want our hash function to generate a random distribution. Now, we may have another problem besides the nature of our hash function. It may be that the data that we have is skewed. And if the data is skewed, we don't have a uniform distribution of values, it doesn't matter how awesome our hash function is, we're still kind of doomed. So that is one thing that we have to keep in mind when we're doing this kind of thing. But yeah, so this is what I talk about here. You may have a situation where a hash function isn't very good. Hopefully that's not the case. But we also may have a situation where the data is not very good for hashing. And so either one of those things could generate a problem where buckets end up overfull. We call that bucket skew, because basically no matter what we do, we're always going to end up with some buckets getting a lot of data and some buckets getting no data. So that's what bucket skew is. And you run into this kind of situation in a number of places. For example, if you do distributed databases where you try to break up the data processing task into multiple chunks that you can execute on multiple machines or on multiple threads or something like that, then you may still have a situation with skew between the various nodes and what they have to do. So this kind of issue can show up in a number of ways, but bucket skew is the one that we're going to be talking about right now. So what do we do when we have a bucket overflow? And again, in memory, what we frequently do is we'll have a linked list of values or a linked list of records that we have linked from a bucket, and so that way it's very easy to handle a bucket overflowing. We just add more records to it. So that's one of the 2 ways that we can do this. Yeah, so this is the other one. So this is the open addressing. This is what Python's dictionaries do, for example. When we get that hash value, it tells us where to start looking, but that may not be where our record is. We need to scan through the hash table, and we may actually go all the way through it and wrap around and come back to the beginning and realize it's not in our hash table. So you can see that that's actually kind of an expensive way of doing it. That's called it's weird naming. It's called open addressing or closed hashing because the other one, overflow chaining, which is the one where you have bins with linked lists in them, is called open hashing or closed addressing. And so I don't know exactly how these terms were chosen, but it is a little bit confusing. So confusing, in fact, that the database textbook got it wrong, and I contacted the authors and said, I think that you have these terms backwards. But anyway, so you can see here, open addressing is I scan through, the hash code tells me where to start looking, and overflow chaining is the hash code tells me what bucket to look in, and it's going to be in that bucket somewhere, and if the bucket overflows, then I have to chase through whatever linked list mechanism that is there for identifying the value. So open addressing works really well, particularly because of caches. We have all these hardware caches we talk about in CS24, and open addressing works really well for that kind of stuff. When you have a list of values, a linked list of values, every time you follow a linked list pointer, you basically generate a cache miss because things aren't packed together so that you can take advantage of other values loaded into the cache line. So open addressing works pretty well for that kind of thing, but we don't like it for disk-based hash data structures because then we have to scan through disk files, and that's no fun. So generally we rely on overflow chaining because that'll tell us exactly what block to look in, not, hey, scan through the whole hash structure and maybe you'll find it. So in general, we'll use overflow chaining for these file-based data structures. And what we can do is when our buckets reach a certain level of overflow, then we say we need to do something about maybe the number of buckets that we have. We need to increase the number of buckets somehow so that we can spread the data out a little bit more uniformly. And again, of course, if we have bucket skew where maybe one bucket's getting all the values because we just have a lot of those values, then that may not help. And so again, we have to detect these kinds of situations. But in general, if we can add more buckets, ideally the values will go into them, and we'll keep all the buckets' fullness below a certain threshold. So that gives us basically our constant upper bound on hashing. Okay, we talked about static hashing before. Basically, static hashing is the really simplistic, I don't know what to do, so I'm going to do something, even though it's not very good approach, where I'm just going to pick a number of buckets. I'm going to hope that I understand my data well enough that I can do this. So, for example, the data set that you work with on assignments 3 and 4 is this store data set. And if you think about it, if you have like a Starbucks company or a Walmart or something like that, probably the number of stores is not going to change very much. And so you could do something like static hashing on the store ID, and that would be okay, because you're not going to have that changing a lot over time. Now, if you have that on employee ID, maybe that's a little bit more difficult, because you expect there to be a lot of employees coming and going when you have a company like Walmart or Starbucks. So sometimes static hashing is okay. We can actually use that. But like I say here, if you have a situation where the data volumes increase over time or data is being added and removed over time, then you may have a situation where static hashing actually starts to behave really terribly. And the fact that you can't increase the number of buckets means that your hashing will, the performance of it will degrade over time as opposed to actually responding to the increased data volume, which of course was the whole benefit of B-trees, is that they can respond pretty gracefully to increasing the amount of data. But static hashing doesn't really have that capability. So what we do instead is we want to have some kind of dynamic hashing mechanism. And all we really mean by that is that we have to have some way of increasing the number of buckets as our data volumes grow, or if we have a situation that we detect where a certain bucket ends up becoming overfull, how can we now change the situation so that we can refactor that bucket into multiple buckets and keep our hash mechanism reasonably efficient? So this is what we mean by dynamic hashing. We need a way of adding buckets to these things. And of course, since this is a file system data structure, we have the challenge that we want to do this incrementally. We can't do it whole hog. We can't, like we do in memory, where we say, oh, the hash table has one bucket over full, so what I'm going to do is create an entirely new hash table and rehash everything in memory. You can't do that on the file system. So we need to have a way of doing this incrementally so that it doesn't ever hit us really hard in the database system. So we're going to talk about two approaches for this. Both of them are really neat, and both of them actually would probably be pretty straightforward to add to NanoDB without too much trouble. So again, if you're looking for CS123 projects, this would be another one that would like make me jump up and down and scream and be very happy. So extendable hashing and linear hashing. These are the two mechanisms that we're going to talk about today. Both are very nifty in their own special ways. Now, when we have static hashing, we have some hash function, and you'll notice here that I have h of k, so that's the hash function that we're applying to our search key. And that is going to map the hash value to some small number of buckets. And so frequently the way that we do this, you may have implemented this yourself, is you have some generic hash function you apply, like a string hash or a byte sequence hash or an integer hash function or something like that. And you apply that to the search key, and then you take the modulo of that with respect to the number of buckets. And so that'll map it to a specific bucket number. And like it says here, it's not very easy to change this hash function incrementally, and that's really the problem that we have, is that we can't take this hash function and change it just a little bit so that now we have one more bucket or two more buckets or something like that. And so this is really the reason why we can't easily update our hashes incrementally. So what we do instead is we update this mapping of our hash values to buckets. And so like I have here, extendable hashing, what we do is we have some hash function, which is basically our h prime of k above. So we just have that hash function, and it produces some large number of values. You can think of it being like the hash code function on Java Lang object, exactly like that. You produce a 32-bit value, and then you can map that somehow to buckets. And so extendable hashing relies on having a bucket address table that we can modify over time so that we don't have to change the hash function, but what we do is we change the mapping, and that allows us to change the mapping incrementally. So let's see exactly how this works. Basically what we do is we look at the top bits of our hash values that we generate. And like I say, we look at the top I bits, and I will start out as 1. So we'll look at the topmost bit, and that will be our hashing mechanism. So we'd have 2 buckets in that situation, or maybe we even only have 1 bucket, because we could have both entries mapped to that 1 bucket. So we have something like this. So you can see that we've already added a little bit of data to our example, and that's why we have the situation that we have. But we have a bucket address table stored somewhere in our data file, and you'll see that I is 2, so we're looking at the top 2 bits of our hash values that we generate. And for each entry in the bucket address table, we say, here is the bucket for search keys whose top 2 bits are whatever. So search keys whose hash value has the top 2 bits of 0 map to the first bucket. But also, if the top 2 bits of the hash value are 0, 1, they map to the same bucket. So you can see that we can actually have multiple entries that map to the same bucket. But then we also have search keys whose the top 2 bits of their hash value is 1, 0, we map to another bucket, and so forth. So we can actually have a way of mapping hash entries to buckets, and we can tune this over time, so that allows us to make incremental changes very easily. Okay, so the bucket address table is going to have 2 to the I entries in it. Right now I is 2, so it's nice and small. So we only have 4 entries. But you can see that we could increment I, and we would double the number of entries in our bucket address table. Then we could increment I again, and it would again double the number of entries in our bucket address table. So how do we use this to do incremental hashing? Well, the first thing is, for looking up, you can see it's very straightforward. We just hash the search key value that we want to look up. And we know I, because that's recorded in the bucket address table. So if I is 2, we say, okay, we only need to look at the top 2 bits of that. So maybe you mask out the rest, and then you look in your table to say, okay, which entry matches the top 2 bits that I have? And you go ahead and follow the reference to that bucket, and that's where you look for the record. So it's really straightforward. It sends us exactly where we need to go for lookups, which is what you would expect a hashing data structure to do. Also, like I was saying, you can have these adjacent entries that reference the same bucket. Now, we can't just have any pair of adjacent entries being the same bucket. We have to have a common prefix. And you'll see why as you see how we update this bucket address table. So in the situation of the first bucket, you can see that since they both start with 0, it's fine. We can have those things sharing the same bucket. But we couldn't have a situation like this because they don't have a common prefix. 0, 1, and 1, 0. We can't have these two things sharing a bucket. So this is not allowed. And again, you'll see why when it comes to how we actually update this thing. Okay, so I is 2. When you have this situation, even though you have I is 2, and we're going to look at the top 2 bits, you can see that that doesn't really matter to the hash data structure because they'll send either 0, 0 or 0, 1 to the same place. It'll be in the same bucket. Okay? So that's perfectly fine. Now the nice thing is, let's say that we're adding values to this data structure, and they keep going into the first bucket, and suddenly the bucket gets too full. Well, you can see that since we have a common prefix, it makes it easier to split that one bucket into 2, because we don't really have to do much to the bucket address table. In fact, we don't have to do anything except just say, okay, now that one bucket that both of those entries were pointing to now points to 2 buckets. And so you can see that we only have to hash a little bit. We only have to update the one bucket. So for example, if that bucket became full, just to show you, we could generate a new bucket with the contents of the first bucket. Do I have? Yeah, I have some pointers and things like that. So we rehash the values. Some move out, some stay, because they still hash to that original bucket. And then we can go ahead and split that bucket into 2 without having to touch anything else. Does that make sense? I think this is totally cool, because now we have a hash table that can be updated incrementally instead of having to do everything every time we decide to increase the number of buckets. Okay? So that's kind of neat that we can do this kind of stuff. And so you can see that when we do split a bucket, all we're doing is saying, well, I want to look at one more bit of the hash code. So before, when we just had one bucket for the first 2 entries, we were just saying, I just need to see that the first bit of the hash value is 0. But once I split it, now I'm saying, well, now I need to see if it's 0, 0, and I go here, or 0, 1, and I go somewhere else. So it's pretty straightforward. There's not really a lot of complexity to it. It's a simple idea, but it's very powerful. Now the way that we figure out what we need to do is you can see that we have this I in the bucket address table, and it has to be recorded because we have to know how many bits we're actually looking at. But every bucket also has its own I, as is indicated here, and that tells us what we need to do when we run into these various situations. So, like it says here, the actual size of the hash prefix necessary for that bucket is what that I on the bucket represents. So I1 says, this is how many bits I actually care about on this bucket. So even though you have 2 entries, and the I in the bucket address table might say, yeah, I is 2, well, the bucket itself says, well, I is only 1 for me, because I only need to look at the first bit. So yeah, I is 2, and I1 is 1, I2 is 2, and I3 is 2. So that kind of gives you a little idea about how this might work. If I need to split the first bucket, since I1 is 1, but the bucket address table's I is 2, well, when I split that bucket, I don't need to do anything to the bucket address table. But if I split the second or the third bucket, well, their buckets' I values are already 2. So when I split those buckets, now I need to update the bucket address table as well. Because I would increase the bucket's I value to 3, but the bucket address table still only has an I value of 2. So I need to actually do some changes there. So we'll go ahead and go through some examples here. So bucket J overflows. So we have this example. This would be splitting the first bucket. So bucket 1's I value is 1, and that's less than the bucket address table's value of 2. So I can split that bucket without having to change the bucket address table at all. Okay? So that's pretty easy. I don't have to do anything fancy there. We already saw that example. Now, if we have a situation, so this basically just goes through this. So when we split a bucket, we're increasing its I value. So when we split the first bucket, we change its value from 1 to 2. So that one is pretty straightforward. And we rehash those records. Some stay and some move. And yeah, so this note is actually very important. You don't just have two things pointing to a given bucket. You'll always have a power of 2 number of entries in the bucket address table pointing to a particular bucket. But you may have more than 2, and so you need to go through and make sure you update. If you have 4, then 2 of them stay with the original bucket, 2 go to the new bucket. If you had 8, 4 and 4, and so forth. It's really quite straightforward. Now, if we have a situation where the bucket's I value is the same as the bucket address table's I value, now we have a situation where there's only 1 entry, and so if we want to split the bucket, we'll need 2 entries, where currently we have 1. And so in that situation, we have to double the size of the bucket address table. So what we do is we increment I, and that doubles the number of entries in the bucket address table. Again, what we're saying is I need to look at 1 more bit in the hash value. And you can see that when we double the size of the bucket address table, we also double the entries. So the first entry would be doubled. So now we have 2 more pointers pointing to the first bucket. We double the second entry. So that's 2 more pointers. So we end up with 4 pointers to the first bucket. And then we have doubled pointers to each of the other buckets. And when we do this, now it's just like the previous situation where we can just split a bucket without having to do anything additional to the bucket address table. So we increment I by 1. And we can split the bucket just like we did before. Okay? Any questions about this? I think this is a totally cool data structure. Yay for hashing without having to do a whole bunch of work. Now, we did talk about bucket skew, and this is where you have to be a little bit careful, because you can imagine a situation where you're like, oh man, I have to split this bucket, and so you increment the bucket address table, and you rehash things, and the bucket is still full, and you're like, oh man, I got to split this bucket. And so you double the size of the bucket address, and pretty soon your whole hash is, your whole hash file is bucket address table. And you keep not actually accomplishing what you want to do. So you have to be very careful about diagnosing these situations. And I think probably the easiest way, I don't talk about this here, but what you can do is when you have these entries in the bucket, you can keep its actual hash, so that you can go ahead and pre-check to see if splitting the bucket would actually give you any benefit. And if it doesn't give you any benefit, then you're like, well, I'm just having one of those days where nothing I seem to do will work. So I might as well just give up and roll with it, because that's just the situation that I have. So anyway, you can basically store a little bit of extra information in the bucket, and that way you can pre-check whether splitting the bucket will actually do you a benefit or not. And if it won't do you a benefit, then you just fall back on overflow chaining. And so you might end up with a situation where if you have really bad skew in your data, you end up having a linked list of pages that you have to walk through, so it kind of turns into a heap file in that situation. What can you do? You can't always win. If you look at it and you say, oh, you know what, the bucket actually does have hash values that might be beneficial for splitting, then you can go ahead and split it. And if it still ends up too full, you can split it again. But the idea is that you can do this process intelligently and stop when it clearly will do no good. And you have to make sure you have that kind of thing in this situation, or else you might end up with your bucket address table exploding in its size, and then that doesn't do anybody any good. Okay? Does that make sense? So that's a pretty important thing to make sure that you do correctly. Now, the observant student will notice that we have tables specifying the mapping from hash values to portions of the data file. And it's interesting that both static hashing and this extendable hashing have that characteristic. They both have to have some storage space somewhere in the data file that is this table. And you could probably figure out, okay, if I have 32-bit hashes, so that's 4 bytes, and I have a record pointer, let's say that you have a page pointer, because that's easy in NanoDB. So that's going to be 2 bytes to say where is the page that holds the records with this search key hash. So now I have 6 bytes. And somehow I have to divide that into 8K or 4K. How many entries can I have? I'm not super good at math, so I'm guessing that's 4K? entries? No, that can't be right. 2K entries? 1K? Somebody help me out. Like 1K entries? I think that's right. So if I have 1K entries, then that can get me a certain distance, but then if my table has to be larger than that, then I'm going to have this mapping span multiple disk pages. And once I do that, then I start having more IOs when I have to look up things against the hash file and so forth. So the size of these mappings can impose an IO cost. And so you have to keep that in mind when you use extendable hashing in particular, because that table can keep growing. So there's another technique which is also capable of incrementally updating hashes, but it doesn't actually require a hash table, which is really interesting. It doesn't require this mapping of hash values to buckets. So let's look at how this works. What it does is it uses hash functions very cleverly so that it can always implicitly determine the mapping from a hash value to a page. So we have a b-bit hash function, like I have here, h of k as before. And so we start out with n buckets. N does not have to be a power of 2, interestingly enough. In the examples, n is 3, just to show you. Okay? But basically, we need some way of mapping our hash values to the bucket that will hold the value that we want. So like it says here, the bucket address space 0 to n. So we start off with h0, which you'll notice we take h of k, so that's just our generic hash function that maps it to a 32-bit value, and we take that modulo n to get 0 to n minus 1. Okay, that's easy enough. That's a good start, but remember, we need this to be able to grow. So we basically generate new hash functions by doubling the previous hash function's number of buckets. So h1 of k will be h of k modulo 2n. And then h2 of k will be h of k modulo 4n, and so forth. So every time, we're actually aiming to double the number of buckets. But the trick to this approach is that we don't actually do the doubling every single time. We only add one new bucket every time we need to expand the hash table. So let's see how this works. Yeah, so we call these things levels, and so that's why we have h0, h1, so it's the level 0 hash function, level 1 hash function, and so forth. And basically, you can easily see that this is the way that we create our hash function. So h of whatever level is going to be h of k modulo n times 2 to the level. So h of 0 is going to be just mod n, h1 is going to be mod 2n, 4n, 8n, so forth. That's pretty easy. Nothing really complicated there. And like I said, we have two hash functions in effect so that we can actually do this expansion. So given level h of level k, yeah, like this is just what I had before. So you'll notice, for example, h1 of k is h of k mod 2n, h2 of k is h of k mod 4n. What if I told you that the original hash value, the generic hash value, is definitely less than 2n? What could you tell me about the relationship between h1 of that and h2 of that? If I told you that h of k, or h of v that we're looking for, is definitely below 2n. Are they not equal? Are they equal? Yay, they're equal, right? So this is a very useful thing. We can take advantage of this. You'll notice that if h of v is less than 2n, then h1 of k and h2 of k, or h1 of v and h2 of v is really what I should say, will be equal. Now, if we're given that h of v is greater than or equal to 2n, again, what's the relationship between these two? Again, you can come up with a very straightforward expression that relates the two hash functions. h2 of v will be, yes, do you want to? It's not just twice, but it's 2n plus the first one, I think is what it is, yeah. because we're modulo, right? So, and since the second level hash function, or I should say the level 2 hash function, since we started at 0, since the level 2 hash function is twice the number of buckets as the first level hash function, is basically just adding on the number of buckets that the first level hash function is considering. That's going to be the new hash. So how can we take advantage of this? Like I say here, when we have a given level, so let's say our current level is 1, and so we have h1 of k and h2 of k, then you can basically say that at least one of these, one of these two things is going to be true. It's not at least, it's exactly, right? Exactly h2 of k is going to be h1 of k, or it's going to be h1 of k plus 2n. And like I say here, if we have like a happy hash function and we have happy data that makes us happy and distributes uniformly and so forth, then we would expect these things to occur with equal probability. Either the two hash functions are going to generate the same value, or the one hash function is going to generate a value that is 2n more. And that's going to happen basically 50-50. So this would be the generalization. So like I say here, h of level I plus 1 of k is either going to be the current level's hash value as well, or it's going to be the current hash function's value plus this n times 2 to the I, the current level number of buckets that we're considering. Okay, this is all set up. We'll see how we use this. Okay, so we have n buckets initially, and in this situation I chose 3 just to show that it doesn't have to be a power of 2. And so we have our buckets here, buckets 0, 1, and 2. And so the level 0 hash function is going to be, well, so we're really simple. Notice k are integers, so our search key values are integers, and we're going to be very simple and say the hash of an integer is just that integer's value. Can't really get much simpler than that. And so you can see that all of these values fall into the appropriate buckets, because 9 mod 3 is 0, 22 mod 3 is 1, and so forth. Okay, so you can see that all these values fall into their appropriate buckets. Now notice that we also have a level. I'm sorry, that's not the thing I wanted to point out. I'm getting ahead of myself. I hate it. It's too exciting. I get ahead of myself. But yeah, so like it says here, if a particular bucket does overflow, we don't really do anything about it immediately. Instead, we just note that we're going to have to do something about this in the future. Okay? So let's say that bucket 2 overflows, we start adding values, and bucket 2 gets too full. Then what we do is we go ahead and roll with it. We add overflow buckets, but we don't really do anything beyond that. Okay? We just note that there's an issue that needs to be resolved in the future. What we do is we expand these buckets in sequence. So round robin is the way that we normally describe it, because we're just doing things each one after the other. Okay? So we have some next value. This is what I wanted to point out. We have next equals 0, and that says when I need to expand a hash table, this is the bucket that I need to split next. Now, when do you decide to do this? I mean, like I said, you could say, oh, the bucket has too many overflow buckets associated with it or something like that. I could keep track of something like that to decide when I need to start splitting buckets. Or another thing that you could do is just look at some various ratios or some metrics associated with the hash table to decide if you need to do this. So it says here the ratio of records stored to the available storage locations. So if you have a situation where you have a lot of overflows, this is going to go over 1 because the available storage locations is going to be some value, and then I'm storing more than that, so the ratio will be over 1. And you say, oh man, I really got to start expanding stuff. So maybe you say when this ratio gets over 0.7, then you start expanding things. Okay, so this is basically what I just said. We basically decide, okay, I'm definitely in a situation where the hash table is getting taxed, so I'm going to go ahead and start expanding buckets. So we're going to split bucket 0. And again, what's the level? So H0 has mapped all these things to the appropriate location. So what we do is we add another bucket, and it will be bucket 3. And we rehash the contents of bucket 0. But we don't rehash them with H0 because that would be dumb. They'd all end up back in bucket 0. So what we do is we use the next level hash function. And that will, hopefully, if we have good distribution of data, send about half of the bucket 0 stuff to bucket 3, and half of the bucket 0 stuff will stay. So like it says here, h1 of k is h of k mod 2n. So now we're moduloing things with 6 instead of just 3. And so 9 modulo 6 is not 0 anymore. Now it's 3. So 9 would end up going to bucket 3. I think I have a few of these things. Yeah, so you can see that 9 would move over. 36 modulo 6 is 0. So that one would stay. And 15 modulo 6 is 3 as well. So that thing would go. And so you can see here that since we're using both of our hash functions at the same time, it allows us to split this bucket into 2 very easily. Okay. And this is all because we have chosen our hash functions so that they're related to each other, like it says here early on in this slide. Okay, so once we've done that, then we can move the next value forward. So you can see that in our header, wherever, we still have level is 0. So we're still using the h0 hash function and implicitly the h1 hash function. Our next pointer is 1, so bucket 1 is the one we would split next, and so forth. Okay? And so we use next to decide what we need to split next. So you can see we create bucket 4. So again, that's bucket 1 plus n. So we go ahead and create bucket 4. And again, we do the same thing. So now we have, again, h1 of k is hk mod 2n. So 16 modulo 6 in this case is, what, 4. So that would go over. 22 modulo 6 is, I'm not very good at math, so I think that's also 4, so that's going to move over. And 25 modulo 6 is going to be 1, so 25 will stay. So you can see again that stuff moves. All right? So we split one bucket. We've made our hash table a little bit happier. And again, once we do this, we move next forward because we split bucket 1, bucket 2 is the next one on the chopping block. Okay? And of course, we do this until we finish the entire current level. So we would split bucket 2 next into bucket 2 and bucket 5. And next would go up to 3, and we'd say, oh, next is now n. So what we do is we reset next to 0, and we increment the level. Okay? So this is what we would end up after having done that. We've split bucket 2 into buckets 2 and 5. Again, doing modulo 6, you can see where values would end up. So 11 modulo 6 is going to be 5, so that would move. 44 modulo 6 is 2, so that would stay. And 2 modulo 6 is obviously 2, so that would stay. And 17 modulo 6 is 5, so that would go. So we end up with the splits that we have there. And once we've processed all the current level buckets, we reset next to 0, so it's like a typewriter, back to the beginning, and we update the level. And then we would go through and split those 6 buckets into 12 buckets on an as-needed basis. Okay? Does everybody understand what's going on here? Again, each time we need to split a bucket, we only split 1. And so you can see that this has some benefits and some drawbacks over extendable hashing. Right? Because with extendable hashing, we can expand the exact bucket that needs the help. So if we have a situation where one bucket starts to get over full, we can directly resolve that issue immediately. But linear hashing doesn't quite have that characteristic. It is able to grow the hash table very smoothly without having to rehash everything. But if we have a situation where one of our buckets far down the line gets full, well, any query or any update that goes against that bucket is going to be slow. And we will eventually get around to expanding that bucket, but linear hashing gets around to solving problems a lot slower than extendable hashing does. Linear hashing has the benefit that we don't need giant tables. Extendable hashing has that problem. So you can see that there's trade-offs between these two approaches. I think if I were going to implement only one hashing file format for NanoDB, it would probably be extendable hashing. because of this characteristic that it's able to address the exact issue or split the exact bucket that needs help. But linear hashing is also really cool. So if I could do just two, I would do both of them. This is pretty neat stuff. Okay, lookups. How do we do lookups against this file format? Because we may have a situation where we haven't gotten around to expanding all of the current levels buckets. So we may have a situation where we have some stuff that's in the current levels bucket, or it may be in the next levels bucket that we split it to, but we haven't actually gotten through everything, so we're not officially at that next level yet. So this was a situation we had before, where we split bucket 0 and 1. We have not split bucket 2 yet, so you can see level is still 0, but we may have data in the level 1 buckets or in the level 0 buckets. So we have to figure out, how do we do lookups against this? Well, it turns out that it's pretty straightforward, because remember that we had this relationship where if I want to look something up using the h0 hash function or the h1 hash function, it's going to differ by some easy to compute value. So between h0 and h1, it's just going to be difference of n. Between h1 and h2, it would be a difference of 2n. h2 and h3, it would be a difference of 4n. So I can actually use that to check the buckets that I need to. Like it says here, h1 of k is also in effect, and it hashes to buckets 0 to 5. Now, bucket 5 doesn't exist yet. How do we know that? We know that bucket 5 doesn't exist yet because next is still set to 2. So we can use next to figure out which buckets we need to actually look at. And so you can see that there's a bit of a two-step process here. It's not that complicated, it turns out. But basically, what do we do when we need to look up a value? Let's say that I need to look up the value 44. I don't know why, but let's say we want to look up 44, and so we use h0, because we know that h0 is the current level. So we do 44 modulo 3, and we end up with 2. So we can look at next and say, has the bucket that this is hashed to been split yet? Right? So I applied h0 to 44, I got 2, and I see that next is 2, and I know it hasn't been split yet. So 44 has to be in that bucket. Now if I want to look at, let's say we want to look up 15. Okay, so that's a more interesting one. So I do 15 modulo 3, because that's h0 applied to 15. 15 modulo 3 is 0. And I say, okay, it could be in bucket 0, but next has already moved past bucket 0. So it could either be in bucket 0 or it could be in bucket 3, because that's h1's version. And that's where h1 could map it to. Like I say here, h1k is also in effect and hashes to bucket 0 to 5. So in a situation where I hash to a bucket that has already been traversed by this next pointer, then I go ahead and just apply h1. I apply the next level hash function, and that tells me where it is. I don't have to go touch disk or anything like that. I just apply the next level hash function, and it tells me where to go, as opposed to the current level hash function. So you can see that you have to use both of these hash functions to do the lookup. Okay? So we're looking at the entry for key value v. We compute the current level hash of the value, and we get a value m, and we compare that to next. If m is before next, well, that bucket's been split. So I go ahead and recompute our hash value using the next level hash function. So m becomes h of level plus 1 applied to the value. And then that tells us where we go. We don't have to do anything else. We can just go straight to the bucket, and it's got to be in there. Unless we have bugs, right? Those never happen. If the value that we computed from h of level is at least next, so it's either next or it's past next, it hasn't been reached by next yet, then the current level hash function will give us the right answer, and we can just look in that bucket. Okay, does that make sense? So you can see that looking things up with this data structure is a little bit more complicated. But it's still pretty nifty that you can take these buckets and split them incrementally. I just think that's totally cool. Okay, so the lookup entry for v equals 22. How do we do this? Well, we could like cover our eyes and not look at the actual disk blocks, because if we look at it, our visual cortexes do much more than just hash it. Okay, so we say, okay, v is 22, level is 0, so I apply h0, so that's going to be 22 mod 3, and I get 1. So how does 1 compare to next? It's not next or greater, so that bin has been split. And so I need to go ahead and use the level 1 hash function, which is 22 mod 6, and that will tell me where it actually is. So I say 22 mod 6 is Donnie's slow CPU processes and gets 4, I think. And we go and look at bucket 4, and lo and behold, that's where it is. Okay. So you can see how this lookup mechanism works. So hash function for the current level, do the math, yay. Now, again, pretend we don't know that clearly 22 is not in bucket 1, because we haven't gone and done the disk IOs to look it up yet, but it's still true. We look at next, and we say, oh, that bucket's already been split, so I apply the next level hash function, and that tells me where to go. And lo and behold, that is exactly where it is. Okay, any questions? So that is linear hashing. I think it's pretty sweet. Okay, so the last thing to talk about, just to wrap this up, we're going to end a few minutes early. Hash indexes are really nice in situations where you do have to do a lot of equality-based lookups. They also turn out to be really helpful when you need to do inequalities. What I mean by that is not equal, because sometimes people use inequality to mean comparisons, like less than, greater than, and so forth. So if you have a lot of equals or a lot of not equals, hash indexes can be really good at making that as fast as possible. And it will actually probably even have the number of disk IOs needed as compared to B trees. Now, if you have a B tree on a data set that's in the hundreds or thousands or even probably millions of records, it probably won't buy you that much. Because a half of 2 or 3 is still 1 or 2, right? So you're not really buying yourself a lot of improvement if you are using a hash index on a relatively small data set. But if you have a giant data set, or basically the issue is if you have a giant B tree. I end up with a giant B tree with a big depth, then a hash index might actually be a big performance improvement. And you can end up with a giant B tree in one of two ways. I have billions and billions of records, or I have really large search keys. If you have either one of those situations, your B tree will be pretty deep. And so a hash index might be a good choice for that situation. Okay? Let me see. So yeah, like I say here, this reality that B trees are almost as good and give you other benefits like range queries is why you don't actually see a lot of hash indexes in the wild. Funnily, most of the commercial databases don't actually have hashing as an indexing mechanism. But most of the open source databases do, probably because of how cool it is. But I believe, you'd have to go look at this for yourself, but I believe that both Postgres and MySQL actually only do in-memory hash indexes. So you'd have to look at that. I'm not sure that they can actually do file system hash indexes. Okay, any questions? All right, so just to give you a little heads up of what we're going to do next. Like I said, the next assignment will probably go out probably tomorrow night or Sunday, because I'm currently in surf recommendation writing hell. Not that I hate doing it, but it is, like, it takes time. And I have to write a few other recommendations. And so I'll probably get the assignment out like Sunday-ish, which means that I'll probably make it due Tuesday at 2 a.m. And we'll obviously adjust everything as the way we did last time. Like, I'll probably have special Monday office hours. And so it's Friday, right? So next Monday will be, oh, what, you're saying no, it's not Friday?
No, actually, next Monday is President's Day.
That's not true, right? It's Monday in a week. Did somebody look that up real quick?
This Monday is President's
Day. Okay, well, if it's President's Day, that's totally awesome. So, if it's President's Day on Monday, then shift everything by 2 days. But anyway, next lecture, whenever the hell it is, and I really don't know. You can tell how in touch with reality I am right now. I was up till 3 a.m. fixing bugs in software. and then I had to get up at 6, so I'm like grumpy and not very sleepy. Hello. But anyway, so whenever the next lecture is, we're going to be talking about index optimizations to plan nodes and the effects and the consequences of using some of these things. We'll talk about the impact on sort merge joins and things like that. So we'll go through some of those things. Very important material to understand so that you can understand why the hell the index you just created isn't being used. So we'll actually try to spend some good time talking about that, and then I'll give you guys a little quiz. There's a website that actually has index quizzes, which is kind of really interesting to study. Hopefully all of you will get a perfect score on it after the next lecture. It's very important. It's not for grades. It's just for funsies. But still, very important stuff to understand. And after that's done, we'll start getting into transaction processing, which is the other super awesome. I see Monday, February. I can't read anything else. Is President's Day? Yay, we all get a long weekend. Okay, so anyway, just be aware that we're going to be going through this stuff, and then next Friday probably is when we'll start transaction processing, which is totally cool. All right, see you guys. Have a good long weekend.